So the last thing we're covering is determinants and Cramer's rule. Determinants and Cramer's rule. Now, determinants, the determinant of a matrix A, so this works for a 2 by 2, is AB, A times D minus B times C. So AD minus BC. So the determinant of A is AD minus BC. So if we look at this first one here, get away from the highlighter, we're doing AD, so 6 times 1/3 minus BC, negative 2 times 5. And this here would give us the determinant. Now we could plug all this here into the calculator, let it do it for us. Or if we did this by hand, 6 times 1/3 is 2, minus negative 2 times negative, or not negative 5, negative 2 times 5 is negative 10. Negative negative makes a plus, telling us the determinant of matrix A is 12. Questions on this here? Now, since the determinant is 12, matrix A is actually invertible. It is not singular, so it does have an inverse. Now, if we look at matrix B, we'll do the same thing. So we'd have 2 times 0 minus negative 11 times 0. Well, 2 times 0 is 0. Negative 11 times 0 is 0. So we get 0. So the determinant of matrix B is 0, which means it is singular. It does not have an inverse. That's it. Questions on any of this here? Any question over anything we've done so far? Now, we can do a determinant of a 3 by 3. I'm going to come back to this here. We've done determinants of 3 by 3s before. And one way that we can do this, and I'm going to write this out and then go back to what we had previously, is in previous years I had you rewrite out the other two sides. And then we took the determinant, we multiplied these three sets of three numbers together. So 2 times 3, negative 3 times negative 1, 4 times 0 times negative 5, 2 times 1 times 5, added those three together. And then we subtracted from it the product of these three groups of three numbers, and that gave us the determinant. Now I'm going to go back to this here. Now this is another way that we can find the determinant of a matrix. Now what we do for this here is we pick a row or column. We pick a column here. So here we're going to pick column 1. Ace of 1, ace of 2, ace of 3. And then we find the determinant of the remaining group. And this seems a little odd, especially how we pick the numbers. Now, if I picked ace of 1, I'm going to take the determinant of this group here. So for ace of 1 times the determinant of this box. Okay. That's just for ace of 1. Now, ace of 2, since we're picking this one, we won't use either one of these, but I'll take the determinant of the remaining group. And the same thing's true with ace of 3, then I'll take the determinant of the top 4. Now to look at this here, we can do the same thing. So we can take the first row here, or I could take the second row, or we could take the third sorry, not rows, columns. The first row, second row, or third column. I said row again. First column, second column, or third column. One of these three here, and do this kind of determinant with it. Now, we could pick the first one, we could pick the second, or we could pick the third. Doesn't matter which one we pick. I would prefer using the third column because the middle number is 0. So if we pick the third column, what we're going to have is a sub 1, 3 times the determinant. So since we picked this one here, we can't use either one of these here. And I think it might be easier just to use the numbers than to use the element's name. So 2 is our first one. Now we're not using 2 or 4, either of the numbers in the first row. We're going to use this here. So we would have 1, negative 3, negative 5, 5. And we're going to add to it the next one. Change colors. Now we're using 0. So we have 0 times. Well, now our determinant is going to be these top two numbers and these bottom two. So we'd have 2, 4, negative 5, 5. And then lastly, the eraser again, we're using the last one, negative 1, times, now it's going to be the top 4, 2, 4, 1, negative 3. To find the determinant of this entire thing. Now for the first one, taking the determinant is kind of nice. We do 1 times 5 minus negative 3 times negative 5. Plus 0 times, we do our diagonals again, 2 times 5 minus 4 times negative 5. And lastly, plus negative 1 times, we do our diagonals, 2 times negative 3 minus 1 times 4. Any questions on what we've done so far? Now at this point again, we could plug each one of these here into the calculator and let it do it for us. If we work this out by hand, 1 times 5 would be 5. Minus negative 3 times negative 5 is 15. Plus 0. Does it matter what any of this one is? Because, I mean, we could do the internal calculations and say parentheses 2 times 5 is 10. 4 times negative 5 is negative 20, which would make it plus. But this whole thing is going to become 0 in the end. Plus negative 1 times 2 times negative 3 is negative 6. Minus 4 times 1. And lastly, we're getting close to the end. 5 times negative 15 is negative 10. We can just say plus 0 plus negative 1 times negative 10. Well, 2 times negative 10 is negative 20. Plus 0 plus, because negative 1 times negative 10 is 10, which tells us that the determinant for this here is negative 10. So if I walk you through this correctly, the determinant is negative 10. Questions on this here? Or, with any of these here, we could type it into the calculator. So we have a 3 by 3. I think it was 121, 242, followed by 0. So we could type the matrix in. Then we can go second quit. Second matrix over to math. The first one, DET, is determinant. Second matrix A. And for the moment of truth, we get negative 10. So that's another way that we could do determinants. Now, especially if you get zeros here, this here can be somewhat of an easier way to do this because we're looking at determinants of 2 by 2s, which are actually not too bad when finding the determinants than they would be for a 3 by 3 using the diagonal method. But the graphing calculator does make this a little bit easier because we could have done this also with the rows, because I could have picked the middle row and done the same thing. So I could have picked 1 times the determinant of our other two here. So it'd been 4, 2, 5, negative 1. Then we would have had plus negative 3 times the determinant of our corners, 2, 2, negative 5, negative 1. And lastly, we would have had plus 0 times the determinant of 2, 4, negative 5, 5. So essentially it's the exact same thing, but instead of picking a column, I picked a row. And for the first one here, we'd have 1 times, because 4 times negative 1 would be negative 4, minus 2 times 5 is 10, plus negative 3. Inside, 2 times negative 1 is negative 2, minus 2 times negative 5 is negative 10, which gives us plus 10. Plus, this whole thing is 0. Well, 1 times this is just going to be negative 14. Plus, well, we have negative 3. Negative 2 plus 10 is going to be 8. I think I got off somewhere. You know, because this should equal negative 10. So I got off a little bit somewhere, but it should work out to be the same. However, the calculator works just as well. Any questions on this here? Either that or we've got to do a little bit different with signs going with rows. Now, with this here, this is Cramer's rule. Cramer's rule is another way we can solve systems of equations. And I find it very interesting that it does work this way. I've not done enough research into why it works, but it's very interesting that it does. Because given a system, a 2-variable, we can also do this with 3-variable systems of equations. If we take the determinant of our coefficients, which is denoted here as D, we can find the x if we replace the two numbers that have x with what it's equal to and divide it by the determinant of the equation. And the same thing for y. Now, this here is going to make a little more sense if we look at it as a whole. So to solve this by Cramer's rule, we're going to use determinants. So x, we're going to have a determinant on top and a determinant on bottom. And we'll have the same thing for y. Determinant on top, determinant on bottom. Now for x, the determinant on bottom, for both of these actually, we will take the numbers in front of the variables. So we'll have the matrix negative 11, 6, 2, negative 5. So we'll have that determinant. Now the determinant on top, the x values, we're solving for x. We're going to replace the negative 11 and 2 with what each corresponding function is equal to. So negative 11 is going to be replaced with 4. 2 is going to be replaced with negative 3. So the x values are replaced with what it's equal to when we solve for x. Well, the y values stay the same. Now for y, the determinant of the denominator, the determinant of the bottom is going to be the same as for x, negative 11, 6, 2, negative 5. Now for x, we replace the x spots with what it's equal to. Well, we're going to do a similar thing with y, but instead of replacing the two x numbers, negative 11 and 2, we're going to replace the two y values, 6 and negative 5, with 4 and negative 3, respectively. Questions on this here? Can we agree that this seems very odd? This seems odd. I've always found this very odd that we're able to take just determinants and switch those two numbers and actually find the x and y value solutions. And what I find very fascinating with this is that it works every time. It's not a setup or something that works just in certain situations or just in certain cases. It works every time. And that's what I find interesting with this. Now, finding the determinants is what we need to do next, and then simplifying. So the numerator will have 4 times negative 5 minus 6 times negative 3. For the numerator, the denominator will be negative 11 times negative 5 minus, going the other way, 6 times 2. Now at this point here, we could plug this entire thing into the calculator. We could just plug the numerator and denominator in. I'm going to just go on and work it out by hand. 4 times negative 5 is negative 20. Minus 6 times negative 3 is negative 18. The denominator, negative 11 times negative 5 is 55. Minus 6 times 2 is 12. 55 minus 12 is 43. The numerator, negative and negative makes it plus. Negative 20 plus 18 is 2. Questions on any of this here? It would be negative 2, yes. That is still a very bizarre number. Yep. Yeah. Any questions on this here? Now for y, we can do a similar thing. We'll do negative 11 times negative 3 minus 4 times 2. Now the denominator of y is 43. Because the denominator for x and the denominator for y when we started with our determinants are the same, yes? So we could have gone and said that it is negative 11 times negative 5 minus 6 times 2. But do I already know what that is? Well, yeah, we got it from the first one, yes? So I have it for the second one already. So I could have done this again, and then reached the same conclusion, or I could put the conclusion in. if we know where it's going. Negative 11 times negative 3 is 33. Minus 4 times 2 is 8. 33 minus 8 is 25. Wow. Questions on this here? Yep. You're good? Yes. And I mean, the fact that we've got such not nice answers is, I think, really throwing us for a loop too. It's because we normally like to do these with nice numbers, but unfortunately, it doesn't always work out that way. Now, when it talks about Cramer's rule, especially on the test, I am going to want to have both of these here at the start, that we have it set up using Cramer's rule. Because there are other ways that we could go about doing this. Negative 11, 6, 4. And I think probably y'all's preferred way is this here. Negative 11, 6, 4. And then I think it's 2. Negative 5, negative 3. Doing this here, second quit, second matrix, our reduced row epsilon form, second matrix A, and we get this here. Math, enter, enter, and it tells us the answer. Because it is a lot easier, a lot faster, but it's very interesting that this does work the way it does. Any questions on this here? So for especially the homework on this here, it's going to want these setups. It's not going to quite make you do the whole work, but it's going to want you to set it up and solve it from there. Now with this here, especially with the calculator, I could, get a highlighter, I could type these in to the calculator and take the determinant of each and divide them. And we'll see that here, especially with a 3x3 system of equation, x, y, and z. Now I'm going to set these up right next to each other going horizontally so we see how they work. I'm probably going to need a little more space than that. As for x, we're going to have determinant of the top and determinant of the bottom. Now the bottom is just going to be the numbers in front of x, y, z. So we'd have 2, negative 3, 5. Negative 5, 7, negative 2. And lastly, 9, negative 2, 30. And even with y, its determinant, the denominator is still going to be 2, negative 3, 5, negative 5, 7, negative 2, 9, negative 2, 3. And with z, 2, negative 3, 5, negative 5, 7, negative 2, 9, negative 2, 3. The determinant of the denominators of all three are going to end up being the exact same. There is no difference between one and the next. Let me get that back. I'm going to borrow that for now. Now the numerators of each, just like with the last one, with x we replace the x values with what it's equal to. So here we'll do the same thing. So instead of having 2, negative 5, 9, In our first column for x, we're going to have 11, negative 6, 4. The rest of the numbers are going to stay the exact same. For y, well, our first column is going to go back to 2, negative 5, 9. However, the middle column with y is going to change to 11, negative 6, 4. And the z values will stay the same. And lastly, with z, well, our first column is still going to be 2, negative 5, 9. The middle column is going to be negative 3, 7, negative 2. But the last column is going to be changed to what it is equal to. Questions on how we did this here? Now with x, y, and z, we have a determinant on top and bottom. Y, we have one on top and bottom. Z, we have one on top and bottom, yes? So we've written out 6 determinants. But how many different determinants do we actually have? We just have 4, yes? Because the numerators all are different, but the denominators are all the same. And when we went over this in Algebra 2, we did this in a calculator because trying to do the determinants of 4 different 3x3s would take a little bit of time. So I'm going to plug them in. And I normally plug them in as A, B, and C as the determinant of x, y, and z respectively. And then I chose matrix D to be the denominator of all 3. So for matrix A, we'd have 11, negative 3, 5. Negative 6, 7, negative 2. 4, negative 2, 3. So we good with the numerator of x. Second second matrix B is a 3x3. So 2, 11, 5. Negative 5, negative 6, negative 2. 9, 4, 3. Second matrix C is a 3x3. 2, negative 3, 11. Negative 5, 7, negative 6. 9, negative 2, 4. Second matrix. So we have the tops of x, y, and z plugged in. Now we just need what would be on the denominator. 3x3. 2, negative 3, 5. Negative 5. 7, negative 2. 9, negative 2, 3. Okay. Now, probably your first thought is that we're going to have to define each determinant for, so for x, we'd find the determinant of A, find the determinant of D, and then divide the two. Then do the same thing for y and z. But one nice thing with this calculator is we do have alpha y equals enter. We do have a fraction. And at this point here, I can go second matrix, determinant, second matrix A, over second matrix, determinant, second matrix. We wouldn't use B, C, but we would use D, which would be negative 77 over 222. They're just batting 1,000 right now with nice numbers. Negative 77 over 222. Then we could go through that process again. We can go alpha y equals enter. Determinant of B over determinant of D. And then do the same thing with determinant of C over determinant of D. or I can select it and bring it down, because the only thing changing is that I don't have A anymore. I have second matrix B. Negative 39 over 74. And lastly, with Z, second matrix C is 449 over 222. Something in me was really hoping that like Z was 3. Just, I don't know, I think that's just a little bit of humor in me that we get to a fraction with a denominator of 222, then we negative 39 over 74, and then we have 3. It's like, not nice fraction, not nice fraction, nice number. Just the comedy in that setup. But that's it. That's all we have to do for this here. And again, on the test, this is really all I'm asking for, especially on the test. I do want the setup, if it asks for Cramer's rule, that we set up how to find x, y, z, and then the values of x, y, z. I'm not asking you on the 2x2s or the 3x3s, or not 2x2, the 2 variable systems or the 3 variable systems to actually work the whole thing out. You can work it out if you want to, or with the 2x2s like we did with this here, you can do the exact same thing. Does that make sense? And if, like these here, you don't feel like these are the right answers, 11, negative 6, 4, because we can always go back and check. -11, negative 6, 4, second quit, second matrix. RREF, second matrix D, math, enter. I can always use the reduced row epsilon form to check and see, are these the correct solutions? Now the nice thing with the homework for this here, it's not going to ask you to find all 3 for the 3 variable systems. It's going to ask you to find 1. So instead of finding here, where we found x, y, and z, it's going to ask you to find, say, y. And you'll break it down. And most likely it's going to have you do this setup here. Then it's going to have you tell it the determinant of the top and the determinant of the bottom's value, and then find the solution for that specific value. Does that make sense? So it's not going to ask you to find the determinant to set up all of this. It's just going to ask you to set up one of them and find its value. But that is it. And that is the last bit of content we're going to learn for college algebra.